Okay. So today my goal is to talk about a bunch of stuff um, of the sort of if I knew then what I know now, right? What would I do differently? And I tried this on with some of my former housemates from grad school and other friends, and they're like, "Yeah, I wish I knew that when I was thinking about grad school, when I went to grad school and stuff like that." So hindsight is always pretty interesting. And what I'm hoping to do is to show you a little bit about some of these considerations that you otherwise don't get to see in the glossy brochures of grad school. Um, and the focus is on PhD, but I'll also talk about masters as well. Okay. And so when you think about what school is, what grad school is, and school in general, hundreds of years ago, thousands of years ago, before all of this infrastructure, it was really apprenticeship, right? And if you think about what an apprentice does, they learn a skill. And these skills, even down to like ancient Rome, it wasn't just physical skills. It was things like philosophy, oratory, law, and things like that, cognitive skills as well. And so, really, education today is a kind of like a mass-produced, the happy meal, if you will, of what used to be called apprenticeship. And in graduate school, at least they still have many aspects of apprenticeship. And when you go to graduate school, and I hope you all do consider graduate school, do it while you're young and energetic and you don't have as many responsibilities. It gets a little bit more challenging, certainly not impossible, but more challenging as time goes on. So let me ask you, what's the whole purpose of a PhD, of a master's, and of the bachelor's, be that BS or BA? What do you think? What do you think? What's the whole purpose? Like, why are you here? What do you think? Why are you here? I mean, not here, but okay. Hmm. Yeah. Hmm. Hmm. Okay. Uh-huh. Okay. You can prosecute this thing called science. You can do science stuff. Excellent. Anyone else? What about that's PhD? What about masters? How's masters different from PhD or bachelor's? What are your opinions? No? You ever thought about that? Yes, yeah. Don't raise your hand. It's you're among friends. I'm done teaching for the semester, so I can kind of relax a little bit. But yes. Hmm. Okay. So you're learning more stuff, right? Deeper stuff. Okay. All right. Um, what about the bachelor's? What do you think? What do you do in a bachelor's? You're in the middle of it, right? What do you do? Lots of stuff, right? What do you think the whole purpose of bachelor's? Yeah. Hmm. Hmm. Okay. So it's about the material, yeah, but it's about a lot of other things. In the bachelor's, you're learning how to answer questions. You learn some material to do that. You learn some technical stuff. You learn some not technical stuff, but you're learning how to answer questions, and there's a lot wrapped up in that. In the master's, you learn how to ask those questions, and then you answer them. And I always get phone calls right as they know. I set do not disturb, and I turned it off, and I only get phone calls when I'm teaching, which is weird. But um, in the master's, you learn how to ask those questions and then you answer them because in the bachelor's, you learn how to answer questions, solve problems, right? But in the PhD, it's a little different. Those questions are new questions that have never been asked before. And that's sort of the difference. But let's kind of look into it a little bit more. So let's think about this thing, we all know and love called computer science. And computer science, when you go to graduate school, you're going to focus more intently on one of these three areas, right? That's how the discipline is divided. And so we have systems. Systems deals with properties of the engineering artifacts, things like your computer networking, things like your operating systems. How do these systems behave? What can you do with these systems? And what properties are engendered by the things that you do with these systems? Then there's theory. Theory deals with the rigorous mathematical characterization and description of the resources consumed by computation. And those resources are two things. It's time, computation time, and it's also space, memory, representation. Certainly, there are other versions of theory that talk about distributed things that involve so-called network complexity. As you share things and exchange messages across the network, how does that impact your computation? And how do you do that so you can guarantee certain properties like consistency or replication or state? And then lastly, there's that third area, artificial intelligence or AI, that deals with the data, right? It's not just the data, it's also certain modalities like sensors or Tableau data and all sorts of other things like that. So when you go to graduate school, you're really targeting a specialization at the master's level, how to ask questions and then answer them in one of these three areas. In the PhD, those are how to ask new questions, right? And that asking the new questions, that's a little bit extra secret sauce that goes into that formula. But nonetheless, it doesn't mean you're only studying these. Some universities, you jump right away into more specialization earlier. But regardless of whether you specialize in systems, theory, or AI, you still have to have a well-rounded education, exposure to all these different areas. And so in the undergraduate curriculum, you take different classes, and in grad school, you're going to explore these things, revisit them more deeply, and you're going to begin over time to see all these beautiful connections between things that you've done in all sorts of classes, even mine. Yeah. Anyway, it sounded funny when I thought about it. But anyways, so this is data science, and data science is about, you can chop it into four areas. There's the visualization, lots of tools, lots of technologies, lots of ideas and ways you do that. There are mathematical tools, primarily probability and statistics. If you're in finance, you might do stochastic differential equations and add multivariate calculus to the mix. There's the data analysis and processing. That's the mechanization of these algorithms that extract insights from your data and do all sorts of processing. And then this last one is the application domain. So let me throw a question to you. Um, in data science, which of these four do you think is where you might spend all of your time, most of your time? What's your opinion on that? Yeah? Application, yeah, you already know. You've seen this before, right? No? Okay, yes, the application domain. Because where you get your data is linked to some purpose. And if you're dealing, say, with agricultural data, you're going to have to learn how agricultural industry works. If you're dealing with healthcare data, you're going to have to learn how the healthcare system and point of care works. So your data is inextricably linked to some application domain, and you really spend, it's not unheard of to spend 65% of your time understanding the application domain, what the data means, how they traffic in it. And then only then can you transform the data to forms that you need for your purposes, for your analyses. Because if I'm collecting healthcare data, I'm not collecting it for you to do your analysis. I'm collecting it for my purposes. And you have to learn my discipline, not the other way around. Okay. Any questions? No? No? Pizza good? Okay. And so what happens with the MS and CS? You do some advanced coursework in the discipline. And so you might take these modern concepts, you start to introduce them, extending beyond what you do in a bachelor's level. And you might even revisit the bachelor's level with more rigor in its treatment. And then you're going to have some specialized training in one of those three areas. That might be seminars or looking at publications, so-called modern work, what's happening right now. Right? Once something makes it into textbook form, it's already been done, sort of on the shelf, ready, right? Most of the modern work is in research publications, things that people are experimenting with where they don't know what the answers are yet. You'll also look at various tools and methods for research, both tools for how you write papers, as well as analytical tools for how you conduct research, how you process the information, how you design experiments. You're going to do major experiential work, a major project, right? Because at the end of the day, you learn how to ask the question, and you have to go and solve this question, how you design experiments, how you plan experiments, what the right analyses are, what's a factorial experiment, how do you look at things, confirmatory versus disconfirmatory research. Because the goal of research isn't just to say, this worked, right? It might not work, but the question then is, why did it not work? So you can have seemingly disastrous results and still call it research, because that's sort of a mark in the sand for other researchers. You don't want to try this because it doesn't work for these reasons. And then you learn how to form questions. It's really, really important how to pick a good question. That's something that you have to be taught. And of course, this last one, communicating the results, is really, really important. If you don't communicate the results in the right way, um, all is for naught, right? You just wasted all of your time and the time of the people trying to listen to you. And so, a master's in data science, you're going to do advanced coursework in math and analytical sciences, primarily probability and statistics and all sorts of tools. You're going to get substantial training in a domain. You have to learn something about the systems and the organizations that source the data that you're dealing with. And then you look at various tools for realizing your models. Sometimes you build it yourself, but even if you call some API, you have to really understand how that thing works. It's not enough to just say, oh, I call this function. You have to be able to anticipate what's going to happen and why. You have major experiential work and master's in data science, and then you go through that experimental design part, the questions, the answering, the communication, and the visualization. And so all of this is the master's, but there are other types of master's programs, so-called professional master's programs. And these things are typically targeted at working professionals. And the goal there is that either, someone wants to get a promotion, you don't want to be an individual contributor, maybe you want to have a staff and be a team lead, or maybe you just want more training in some area like chat GPT and prompt engineering, for example. And so with that, those professional masters, you're not necessarily doing research per se, but you're still doing substantial engineering and applied work. And so you're going to do advanced coursework, possibly in one area, most likely in one area. Sometimes it's more than one area of data science. And then you're going to have training in the tools, and the problem solving is applied to a specific topic. A former student of mine, she's getting a master's in data science at University of Washington, UNH, if you know her, and she's focusing on business and finance. And so she's learning about economic time series as well as some of the time series models that they use in addition to the machine learning and the more data sciencey type of stuff. And so it's to a specific domain because ultimately the goal is to advance your career, be that from individual contributor to a director or something where you're in a position of leadership. And then, of course, the professional master's adds an aspect of project management and implementation. You're focusing on solution development. Okay. Any questions? No? All right. And so, what is the PhD? You notice there's a lot more bullet points here. I'm not going to go through all of them exhaustively, but you're going to start with advanced coursework. And this advanced coursework is going to be in all the three areas of computer science because the goal is to raise your literacy level. And any PhD in computer science should be able to teach the intro and the core course in any curriculum across all three areas, whether they like to or not, right? You might be a little rusty in some topics, but you should be able to teach any undergrad course at the intro level at least. You're going to do training, and this training is in the planning and execution of experiments. You don't just do an experiment, you have to plan it. What are the questions? What are the domains? What are the tools? What are the right questions? What questions have other people asked? What were the answers they had to those questions, and why? You're going to also get training in managing people. A lab has a lot of moving parts, and the culture in the PhD, it's a laboratory culture. At the end of the day, the PhD is a research degree, and there are many mechanical things that you have to learn. One of them is in managing people. Now, that might be as a PhD student, maybe you're managing master students or undergrads in your lab, or maybe you're helping to manage undergrads in a course that you're related to. You're also going to have to learn how to teach in a PhD program. And that's done either as a teaching assistant running a lab section, or maybe you're training somebody in a lab. You might have an area of research in the lab, and it's your responsibility to bring the more junior members in the lab up to speed on that particular thing you're working in. That's both the technical side as well as the practical side. And then of course, this is really important, reading and reproducing contemporary work in your area of specialization. It's a really important skill to be able to read a paper and reproduce those results. And if you've read through a research paper, there's a lot of stuff that they don't include. And how to make those decisions on the stuff that is effectively between the lines, not explicitly written, is a really important skill. And in the beginning, it's going to be a bit of a challenge, but over time, as you accumulate more tools, more technique, more experience, it gets easier and easier and easier. So that's part of the learning curve that's particularly steep in any PhD program. And then, of course, this identification of key unsolved issues. As you start to read the research literature, you can get lots of ideas. You're not the only smart person in the world. Lots of great ideas a lot of people have had. And so being able to take all of these different approaches and register them someplace to know what is addressed, what is not addressed, and where what you're trying to do stands within that marketplace, so to speak. And so this ability to identify key unsolved issues, that goes to the creation of new science. And that's the barrier to entry for a PhD. You're learning how to ask new questions, things that have not been asked before, and answering those questions. Any questions? No pun intended. No? All right. And so for me, yeah, sure. Mhm. Yes. In the PhD program, generally the first year or two, you're taking classes, and then after that, you're full-time researcher. And that full-time researcher can be anywhere from 3 years to 5 years, depending on what you're doing. And there are lots of factors that can impact that. Well, one of the worst ways to tick off your PhD advisor is to keep taking classes, right? And I'll talk about that more because at the end of the day, for a PhD, they don't ask you how'd you do in your classes. They don't ask you GPA. The first question, oh, I have a doctor. What was your research contribution? What was your contribution to human knowledge, to society? That's what matters. And so I would rather have a B student who's an excellent researcher than an A student who's just a good student and not a researcher. Because at the end of the day, I want that research productivity. So to answer your question, yeah, you're going to take some courses, and depending on what you're doing, you might have to go off and take other courses. So if you are in an area of, say, computer science, where certain statistical tools are necessary, you're going to go off and have to take some graduate stats courses to augment what you're doing in computer science. But at the end of the day, generally 2 years or so, you're done with courses and you're just full-time in research because most of the learning happens in that bullet point about reproducing the research. Because you'll find, oh, you're doing SISR. What's SISR? Sequential importance sampling, resampling. Oh, let me go pull a paper on that. Oh, let me read this. Let me try. You're doing a lot of that self-education from the research literature, the model. Okay. All right. Any other questions? No? No? And so then you're also learning how to form a good question once you identify a key unsolved issue, and then you're proposing a solution. That's the hard part too. Question, yeah, yeah. No worries. That's ah, oh, it's a tool, And I remember back in like the 2000s when statistical search engines came out, like Google, right? Before in the early days of Yahoo, it was just an internet directory. People would post URLs to stuff, and you just slice it and drive down. And then InfoSeek was the first statistical search engine, and people were like, oh, it's people are going to cheat, it's plagiarism, and it was the same argument. Um, AI systems and large language models, essentially, they're really big statistics engines. And at the end of the day, and I've even found this with my own research work with ChatGPT 3, it doesn't do well when you ask it to synthesize new things because all it's looking for is patterns and word occurrences. Yeah, auto transformers and all that stuff, and you throw a lot of data into it. But at the end of the day, if you ask it, and I'll give you a concrete example, if you tell it, a knowledge task like, um, what's the difference between interquartile range and standard deviation, right? It'll tell you that. That's just a recall, information recall. But if you ask it, create me a new data set that illustrates the difference between when standard deviation is worse than interquartile range, it falls apart. It'll sound really good, right? But it's not that good for synthesizing new knowledge. That's something else. So to answer your question, you could try. But I'm not so sure about how successful you would be because reading the research literature, there's a lot of unwritten stuff that you have to synthesize in order to slog through all of that. Did I answer your question? All right. Any other questions? No? And then there's the design of experiments. A research experiment, it might take you 6 months to design it and another year to execute it and get results. It's a long-term thing, and prosecuting science requires certain skills, including writing stuff down, right? Your research notebook. And then, of course, the interpretation and communication of results. And this last one, the projection of future impact, is really, really important. You have to understand where science is going, how your work fits in, but what contributions this makes possible. Okay? All right. And so this is on the input when I started the PhD program at UMass. And that's on the output when I was hooded and got my degree. And, you might think, gosh, you start here, it's a line, mx plus b. This slope isn't too big, it's a zero slope. But that's absolutely wrong. It never happens that way, right? This pathway looks more like this. There's a lot of stuff that happens along the way. And my hope in, talking to y'all today is to kind of tell you the things that I wish I knew then that I know now. Okay. Some of those things, not all those things. But nonetheless, you wonder, what the hell happened here? Why is that past so messy? It can be very, very messy, messy in ways that you don't anticipate, but also messy in beautiful ways that enable all sorts of wonderful things like choice in your life. Like I tell some of my students, there's no more beautiful thing in life than to have choice, right? And how you do that is by preparing yourself in ways. And you can either stub your toe and fall down, or you can get some advice and hear about those mistakes before they happen. So that's my hope today. And so there are all sorts of milestones along the way. You can be thinking about a PhD program or graduate program. Okay. You have to think about it first. Then you have to put some action to that. You have to actually apply. Okay. You push out some applications. There's a bunch of considerations. How do you decide where you're going to apply? How do you know if you're going to like it? Because not everything is for everyone. And that's okay. Right. But understanding how you match yourself to that situation is a really important thing to consider because a lot of people don't do that. So then, congratulations, you get in. Then you have to select one. It just got real. Like, oh, wow, I was accepted, right? And you apply, you want to be accepted. But when those acceptance letters come in, then it's a whole different thing. Now you actually have to make a decision. So how do you select a program? And then after that, if this path works right, then there's the early years. There's going to be some stuff you're going to encounter in the early years that nobody tells you about. Now, at UMass Amherst, where I did my PhD, at the time they were ranked top 10 in the country for what I was studying. And the cohort that I came in with, it was 42 of us, right? And so at the end, there's like another picture, 5, 6 years later, and everyone's like, kind of broken down and looks tired and stuff like that. So there's a lot of stuff that happens, particularly in the early years. 19. Yeah. A couple of things happened. Um, uh, some kind of went off the industry. Some got really frustrated and just left. And all sorts of things. One person I'll never forget, Dr. Hannah Blau, she finished. She got hit by a car. And so she had to learn how to walk again. And so if you want to see what tough is, that's Hannah Blau. Unbelievable. And she eventually finished. She had to take time off and, she walks with assistance now, but it's doable. If you can get hit by a car and still finish, there are some things that you can circumvent. But the hope is that you try to optimize your chances of success by just being aware of some stuff. But half of those who dropped out, it was to go off why am I doing this to myself? I just want to go off and get paid, right? And that's fine too, right? Some others, it was frustration. It can be a very hard thing if you've never been through it before. And the hard part, you have to learn how to do science while you're doing science. How the hell do I do that, right? You're kind of learning as you go along. Okay, so there's the early years, and then there's that part I call the apprenticeship. That's where the real learning, not the book learning, that's where the research learning starts. And it's very different from book learning, right? And I'll talk about that in more detail. And then after that, then there's the proposal. You can almost see that end in sight. That's where you start to outline what your contribution to science is going to be. And then there's the thesis. Okay, you go off and do the research. Now you're talking about it, but you're not done yet. There's the end game. You start thinking about what you want to do next, that preparation to meet those opportunities before you're actually done. And it usually starts a year before you think you're going to be done, right? And there's all sorts of considerations for that because you want to make sure you're tuning a little bit of this to that. I remember one classmate, Trevor Stroman, he had this thing called tuple flow, and he tuned it specifically to get a job at Google Research. And Trevor got a job at Google Research, and he implemented tuple flow, and it's within their scatter reduce the Hadoop stuff in there, right? It's a particular type of algorithm to scale up computations in a distributed environment. So you can actually deliberately make choices at the thesis part by thinking of the end game ahead of time, what your landing spot is going to be. Okay. Any questions? No. And when you finish, that was one of the, not the top 10, probably number 11 happiest, best days of my life. The happiest, best days have nothing to do with what I do as my day job, right? But nonetheless, I have no idea who's photobombing me just over my shoulder. But nonetheless, this was literally when I was finally done. And to date, I still save that email from way back when. Congratulations, the graduate school has approved your thesis, Dr. Holmes, right? Anyways, and it's kind of anticlimactic, right? Along the way, I thought I was going to change my license and credit cards to say Dr. Gary Holness. Yeah. And then you graduate, you're like, yeah, whatever. I just want to get a full night's sleep. It's pretty simple and free pizza. But nonetheless, there's this end game. And you have to think about these milestones. And what I hope to convey to you is some of those things they don't tell you in the brochures, considerations among all those things, and some of those experiences that'll happen along this twisty, turny, wandering path, which is your PhD journey. And everybody has a story. Everybody. It doesn't matter who it is, whether that story was finely tuned or whether it was very messy and wiggly as we speak. Another colleague of mine from grad school, Matt Radigan, we were like, why are you doing that? He joined Obama for America campaign, and he was one of the people integral in introducing data mining into political campaigns. Go figure. And now it's a big deal. But when Matt was doing it, it wasn't a big deal. Now he's back at UMass, just hanging out, right? So there's lots and lots of things you can do because this PhD, these skills you find are very transferable, even if you end up not doing computer science at all, right? Lots of transferable skills. Okay, so let's think about grad school. Let me ask you. Now, this is focused on the word ideal. When do you think is the ideal time to start considering graduate school? When do you think? Yeah. Hmm. Okay, that's a good answer. Any other ideas? Yeah. So right at the end towards, yeah, freshman year. Oh, you saw this before. Freshman year. Oh no, I'm a junior. All is lost. And this is the ideal. And the reason why I say freshman year, it has to do with choice, right? When you're a freshman, you have more choices. Okay, so the BA or the BS, and not to be insulting, it's sort of the infant level in your technical and academic development. Well, unless that's kind of insulting. I'm a grown adult. Yes, you are in the eyes of the law. You can be drafted, and maybe in a couple of years. You can buy a drink legally, and all sorts of other things. You can vote and stuff like that. That's wonderful. But in the BA/BS, you develop some key skills. You learn some technical bits. Great. You learn some operating systems. And if you take my class, we just learned ARIMA and SARIMA, right? You can ask these two about it. But nonetheless, you learn some technical things, but you also learn things about yourself and the world around you. You might not have known that you're a night owl. Maybe in high school you thought, or you were an early morning person, or you like to learn in certain ways. In college, you're not just learning about the technical stuff, you're learning about yourself and how the world around you functions in ways that you might not have realized. You learn the curriculum. There's certain required things like systems, AI, theory, and computer science, certain knowledge units. You also really sharpen up your critical thinking skills and problem solving. Because in college, it's not just things that are linear, right? Things are going to require you to think really hard about a problem, and you develop various techniques and strategies for how to think about things. In my assignments, my projects, and my classes are experiments. And I see the difference between the 200 level students and the 100 level students. The 100 level students are disturbed that I'm not telling them exactly what to do. Well, what should I do, Dr. Holness? You choose and tell me why, right? And so that critical thinking is something you hone as an undergrad. It's really, really important. In addition to examples for reduction to practice, you build things, you analyze things, you learn how to put them together. You learn about the choices you make for components. When you put these things together, what does that engender for the system that you built? All of that happens at the bachelor's level. So why freshman year? If you mess up, you have opportunity to recover and make other choices. If you decided you can't stand multivariate statistics, guess what? You can do something else. The earlier you make your choices, the more abilities and it gives you and more opportunities it gives you to recover and correct course. If you wait until the last minute, meaning, and it's not, you know, to say that you shouldn't wait until senior year, second semester, thinking about grad school, but you haven't set yourself up with the ability to make those choices as easily. It's going to cost you everything. It's going to cost you something, your time, your effort, your money, your energy. And I'm always honest with people I advise about what that cost is. Yeah, you can succeed, but you have to commit to yourself, not me, commit to yourself that you want to pay those costs. So starting early makes that cost cheaper because you can change. Starting later, that's going to come at a cost. Maybe you take a summer where you take other courses. Maybe you take an extra semester and pay, what is Clark charging now? 50 something thousand, something like that. Maybe you pay more for it. So, but there's a cost. And it's not to say that grad school is a lost hope if you wait until later. It's just starting earlier helps you with that flexibility, right? So if you're starting later, still good news, but there's a cost. And I don't want to sound, oh, he's being so, gloom and doom, because I'd be lying to you to tell you something else. And I care too much to tell you, what you want to hear. I'm going to tell you what you need to hear, right? Okay. And so more opportunities. So let's think about this applying. So computer science departments, computer science is a discipline in general, grew out of two traditions, out of the engineering tradition and out of the math tradition. You notice in some universities, like at UMass, computer science department, now it's its own college, the College of Computing. Um, but many universities, the computer science department is in the School of Natural Science and Math, right? Others, it's in the School of Engineering. Now, that has to do with the tradition out of which that computer science department evolved. And those that came out of the engineering tradition, very often you have to build it, right? And it's not just about you have to build a system, but you test these theories in an actual working system. Your prototype supports the science. That's really, really important in the engineering tradition schools. And how these choices that you make in this prototype, your experimental apparatus, what it gives rise to in terms of the outcomes that are possible and why. In the math tradition, they take models and they're proving things about aspects of the system. And with this, you're looking at what I like to call the physics of information. You're not dealing with just data and outcomes or what the system does. You're trying to understand how the parts interact and what those forces are inherent in those interactions and what that means to the overall system or some concept or thing you're trying to prove. Now, it's not to say this is a hard and fast rule because some departments do more of engineering, some of more of the math tradition, some do a little bit of both, some are slightly in one direction or the other direction. Some examples. Stanford is very much an engineering tradition in computer science. University of Michigan is very much an engineering tradition. MIT, Virginia Tech, UPenn, and Penn State. Berkeley, Brown, UMass, and NYU are more so in the math tradition. It's not to say no building prototypes happens in UMass. Some of them build some prototypes, but their tradition is more, I'm going to prove something about my system. And so if you're someone who likes to build things, really loves to build things, it might not be the right match at a more math tradition department. If you're somebody who likes to prove things and you love this beauty of how these things interact with one another and what you can prove, well, maybe an engineering school is not your place, the engineering tradition. Now, this is not to say, Stanford, they do some really good theoretical work improving things. But if you look at all the PhD thesis that come out of Stanford, you'll notice they tend to build substantial prototypes. Okay. So that's one of the considerations for applying. Now, the other thing to really consider is the PI's posture. PI stands for Principal Investigator. That's the term ascribed to typically the director of a lab or a research effort, and this person is in charge of that research. And so research is funded typically with government money. And that could be from a bunch of different sources. They could be from foundations. And how this, cycle of research life goes, you start with an idea, right? You generate an idea, you go out and find funding for this idea. So you're doing some fundraising. You develop a proposal. You say, I have a great way to address this problem using this idea to solve that problem that you set up in your call for proposals. You submit the proposal, and then that proposal is judged by a series of scientists. And I've served on NSF review panels. It's an interesting experience. Then, congratulations, you get the grant, you manage that grant, and you conduct the research. And so this is what the PI's posture is, their view of science. And when you join a group at a university as a graduate student, you're joining a research lab, right? And so something to keep in mind is the experience of the principal investigator, because this person is going to shape your success in receiving admissions. And I'll talk about that a little bit more. Now, this is theoretically what it looks like. This is what it is in practice. Research and competing for research is a brutal combat sport. Just because you're small Clark University, they don't take it easy on you. You're competing against MIT, Stanford, Berkeley, Michigan, Penn, Brown, etc. You're competing against universities that are much bigger with more resources, far more horsepower, and you're also competing with universities that are much smaller, much less research horsepower. You have to step up and compete in order to win this research funding. It's an intense competition. And so when you apply to graduate school, yeah, you might apply to the School of Graduate Studies, maybe to the department. You're really applying to a research lab. And keeping that in mind, when you apply to a research lab, you need to be aware of what they're doing. Because what ends up happening, and I've been a graduate program director in my previous institution, you get all these applications for the graduate program, whether master's or PhD. Generally, it's the junior faculty that they make sit in a room and review all these things. You go through all these applications, and then you have this set of criteria about who you're going to accept and who you're going to reject. Now you have that acceptance pool, and now you go through all the research labs and say, hey, you have a vacancy for a graduate student. Is this an attractive candidate to you? So it's directly related to the needs of their PIs in the research lab, shaping to a large degree your decision for acceptance or rejection. If you have two candidates and one has been doing all of this wonderful statistical analysis and the other is implementing all these systems, if I need these statistical analyses in my lab for my research projects, guess what? I'm going to say we want this person, even though they're both suitable candidates. So you want to let that idea of being a member of a research lab. You're really applying to a research lab. You're not applying to a department. You're applying to a research lab. And that's what happens behind the scenes. And so, how do you make yourself attractive for a research lab? One is your course selection, right? If you have two versions of math, and not to denigrate business math, but if you have business math or business statistics versus calculus-based statistics, take the calculus-based statistics. It's more rigorous, and that's more needed in the research lab. Look at the strength of your curriculum. Yes, you could take it easy, but you want to see what do these organizations do they need. Look at your project work, opportunities to get involved in projects, because those reducible skills, let's say I need someone who needs robot operating system. Heck yeah, I'm going to choose somebody for my lab if they know ROS already, because that's of value to me, right? And so internships, meaningful work experience. It means you know how to make code that's reliable and scalable. And you can do that, and you really know how to use these language systems, which is important for implementing these prototypes. Maybe you studied abroad, right? So you can manage all of that, and you can do it in another country. And in graduate school, you can have people from all around the world. So that helps your people skills and your ability to get along with a lab culture. And these soft skills are really, really important. Your communication skills, your time management, and your organization. And then you're also oriented in your discipline. You know where the discipline is going. You know that large language models are pretty hot right now. And so something with LLMs might be of use. And so keep in mind that when you're thinking about a graduate program, consider the PI's posture because you're really applying to a research lab. Even though it says you apply to the graduate school or to the department in some cases. It's really the research lab vacancies that drive who gets accepted. Okay. All right. Any questions? Ah, that's a great question. You can kind of read between the lines, right? If you do reconnaissance on their websites, you can see which students are the senior PhD students, and there might have stuff on the website about their proposal or they finished their proposal. And if you finish the proposal stage, you know that you're in the thesis stage. You're at the end game. And then you can also look at when they started grad school, because some of them will have their CV up, curriculum vitae, and they'll say, oh, I've been a graduate student at UMass Amherst since this date, and now I'm a PhD candidate, right? I'm all but dissertation. So you know those people are towards the end. You also, and I'll talk about this a little bit later, can do some investigation on who has active funding. Because if you know if someone has active funding and that funding is very early in its period of performance, and you know someone's graduating, you know they're going to have vacancy, right? So there's all sorts of things. They're not going to say, I have vacancies for these people. Some will say that on the websites. I'm looking for two graduate students. Please don't email me unless you've actually been accepted. Some of you see that posted, right? And you really shouldn't email them unless you've been accepted because they won't even answer you. Because if you think about their perspective, you're getting probably, dozens of emails a day, literally, from people trying to do the same thing, right? They're not even going to look at it. It's just not scalable. Did I answer your question? Okay. And so you also have to think, and this is not intended to be harsh, the value that you bring to the research lab. I want to know, can I trust you? And I use this word specifically, can I trust you with the stewardship of hard-won research dollars? And those dollars are taxpayer dollars that the government, oftentimes it's the government, has invested in the lab's vision. And this is a zero-sum game. And I take research funding very seriously, and most PIs do, that money that I got was money that someone else didn't get. It really is a zero-sum game. In addition, because it's taxpayer funding, money that we get, 100,000, 500,000, a million, is food assistance or housing that someone else didn't get. And so it's such a brutal combat sport getting these research dollars because the competition is fierce that I want to know that you bring value, you add something to my lab, and you want to choose your courses and present your portfolio, whether it's your work, your projects, etc., publications, that shows me that I can trust you with my research dollars. Because the research dollars that you enjoy is directly related to the success of students who came before you. And I'm thinking about that constantly. Moreover, the research dollars in the future are going to be dependent on your success. And so, to your research advisor, my success is inextricably linked to your success. So I'm going to protect that for dear life. You have to show me that you have value. Is there something that you bring of value to my research lab? Because I can't afford to just spend money, invest money, and not get a return, right? So that's always on the PI's mind. And so it's really important to show the value that you bring. You can't just say, these are the things I did. You have to tell me why it's important. If you did something spectacular, then tell me, make it measurable. How was that impacted? If you understand Ross, do you really understand Ross? Tell me what you've done in Ross. How was that valuable, right? You have to show me the value that you bring. And so one of the things you can do is some investigation. If you go to nsf.gov, to a harder degree, DARPA and Army and all those other places, who has active research grants? If you go to NSF, because it's taxpayer dollars, they publish all of the active research grants. Who's the PI? How much it was, when it started, how much they've spent at this moment. And so if you see somebody with a lot of active research grant, guess what? They have funding to hire. And it actually outlines what the summary and the goals of the project was. So do some of your homework and also who's graduating a student. If a student is in this designation all but dissertation, they're closer to the end game and they're going to be out of there probably in another year to 2 years, right? And so you can also find out who has money, right? Now, this money can come from different places, can be from a foundation, from National Science Foundation, from government agencies, military, all sorts of different locations. But you can, at least from the NSF side, find out who has active funding because it's that PI with the active funding who's going to be in a position to hire people. Okay. Now, some advisors, some PIs, like one of my advisors from UMass, he's near retirement. So he still have access, has active research grants, but he even says on his website, I'm not taking on new students because I'm just going to take the students I have, graduate them, and then retire, right? And so that's one thing to check for if somebody's towards the end of their career and deciding just to wind it down into retirement. And so the other thing to think about, and I'd never thought of this until I was actually at the PhD program, examine the university's bank account, their endowment. The endowment is this big bank account, and some of it is earmarked for specific purposes, but it really enables the resources that the universities have. For example, Stanford University, they have a particle accelerator on campus, atom smashers for doing serious physics work. Their endowment is probably like 8 or 12 billion dollars. And what that means is you have flexibility to have all the nice things. Because as someone once said, I love this quote, grown folks understand if you want nice things, you have to pay for it, right? And the endowment adds that stability so that you can buy those nice things. And so the endowment matters, and you can always check the endowment of a university. Things like state schools are a little bit different because they get regular funding from the states, and states have pretty nice big budgets. But you want to check the endowment because that translates into the quality of facilities, research facilities. Do you have big compute clusters? Do you have all these amazing walking robot platforms? Do you have this specialized equipment like a scanning electron microscope and you can actually split genes and do all sorts of stuff right there on campus instead of having to travel someplace halfway around the country to do that? Do you have observatories right there, or do you have to spend the summer in Hawaii, which is not bad, to go use some of their telescopes and their observatories? And so check that endowment. Endowment also enables research support services, a machine shop. If you're in physics and certain other disciplines, you need a custom piece of equipment, you go to the machine shop, spec it out with the machinist, comes back a week later. That's what endowment enables because they can afford the facilities and afford the personnel. A makerspace, like how we have a makerspace, money, all of these things. And it's not only about money, but research apparatus is fed by money, right? You need money to do that. Also, staff programmers. You can hire things like staff programmers. If you go to MIT Media Lab, it's like a medium-sized company over there. As a grad student in the media lab, you might have 2 or 3 professional software engineers helping you implement the stuff you need for your research. Well, that's kind of nice. It helps you to be more productive much faster. Things like postdocs, right? postdoctoral researchers. If you're on your way out, many universities with a lot more money, they will hire you on as a postdoc so you can stay on, do more research until you're ready to go out. Or postdocs to come in who bring expertise, pay them to help you with your research. All of that is fueled, among other things, by the endowment. And then facilities, things like good gathering spaces, nice facilities. Are the buildings modern and comfortable, or are they breaking down? University-owned housing. There are some universities that have beautiful apartments for grad students, and you can rent it for several years, and it's competitive with the area around the school. University transportation, things like that. There's some universities that have university-owned bike shares, which is kind of cool, right? You see that more on the West Coast. But all of this matters, and looking at the endowment is sort of a proxy for other things like the library holdings. Right? Do you have access to journal publications, which is really important for your research, right? So look at the bank account. And so university level funding is also enabled with a big endowment. Things like tuition waivers. They give out this monopoly money, this funny money, say, we're going to pay your tuition. Or if you need extra money because you need to stay longer to work on your dissertation, oh, here's a university scholarship, right? To sustain you for an extra 6 months. All of this is enabled by the endowment. So don't overlook considering the bank account that the university has. And they will all tell you how big the endowment is. It's a point of pride for them. Okay. Any questions? So in your considerations, don't exclude the bank account, piggy bank. And then make an honest assessment about who you are, right? And that might be tough. And all is not lost. If there's some areas you need improvement on, yeah, with time, you can improve on them. That's the good news. How strong of a candidate are you? What's the strength of your curriculum and your course selection? Did you choose to take calculus-based statistics or did you take business statistics? Then go back and take the calculus one if that's something needed. Examine the competition. Look at the statistics for the admits for your graduate programs that you're targeting. Are you an outlier? Or are you close to the mean, so to speak? Look at schools in three different categories. Your so-called dream schools, if I got in there, oh my goodness, the target schools, and then a couple schools that are the quote unquote safety schools, just like you do in undergrad admissions. Because if you want to go to a PhD program or graduate school, yeah, go to the best one that you can, and don't be afraid to change things that you think you need improvement on. Everybody likes a comeback story, right? That's the good news. And so rankings matter, yeah, and you'll see advertising like US News and World Report, but the discipline rankings are much more important. So one school might have a big ranking because they're well known, but their ranking within, say, machine learning or reinforcement learning might not be consistent with their US News ranking. US News and World Reports, they're trying to sell magazines. No more, no less. And don't believe me, look at their ranking criteria. And one of those big areas is reputation. What is reputation, right? So really look at how well known they are in the discipline, not just these publications that talk about general rankings, because often they don't coincide with what the discipline stuff is. Okay. Any questions? No? Yeah. Yeah. Hmm. 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 Yeah. Yeah. You can ask people. So I had a student, she's now in grad school. She got accepted to a couple PhD programs, and she asked me about a couple of them. And I said, well, they have a good name. I'm not going to mention the person, not going to mention the schools. They have a good name, but for cybersecurity, you're better off going to the school in DC because they're doing a lot of cybersecurity, and some of the best cybersecurity work is being done in the sphere of influence of government, right? And so she ended up going to that one, and she's doing phenomenally well, right? And so ask people in the discipline. Take, for example, machine learning. People, MIT does a lot of great work for reinforcement learning and certain aspects of machine learning. UMass Amherst is much, much better. And if you go and ask someone at MIT, they'll tell you the same thing. A lot of pioneering work in, in reinforcement learning was done at UMass, right? And so the first statistical search engine, which powered InfoSeek, that um, natural language processing stuff was done at UMass, the Center for Intelligent Information Retrieval. And so the thing is to ask people in the discipline because they'll tell you, if you're going to do this, yeah, that's fine, but you want to think about this place because they have a pretty good provenance and a really good research group for that area. At one point, and I'm talking about UMass a lot because that's where I went, right? So, one of the leading statisticians, Don Guimond, who invented Gibbs sampling, was at UMass Stats Department, and UMass kind of offered people early retirement, so they lost like half their stats department, which was a sad thing. But to answer your question, you can read these stats, and some of them will look at things like publication output, impact of the research, but also ask people in these disciplines, and they can tell you as well. Hmm. Ah, um, it's usually, I mean, at schools, at really big schools, how they fund students, nobody who gets a PhD in computer science in the US pays for it. You pay for it with your effort, right? But not with your wallet. And I see. There's none. It's global scope. It's global scope. Yeah. And so you really want to position yourself in terms of your curriculum, your project work, and showing your value to the PIs of the labs. That's how you get admissions. Question? The master's is a wonky thing, right? Because some universities, and it's hit or miss depending on the university, some say we will fund all graduate students in computer science. Hard stop. Others say we will only fund you if you're a PhD student, right? And some people do, you could say it's ethical or unethical, whatever. They say, hey, I want to be a PhD student. And then once you get your master's along the way, you say, oh, I changed my mind and leave, right, to get the funding. But some schools, they've caught on to that. UT Austin, you just get a PhD. That's it. Some of them, they give you the master's and PhD right at the end, right? Because they know people try to do that, right? Some, Stanford, your master's in computer science, they're not going to pay for it. You pay tuition to Stanford. And it's not that Stanford needs the money because they know you're in Silicon Valley. And with a Stanford master's, you're going to get a job paying 400K a year easily. No problem in Silicon Valley. So they can do that, right? And so it really depends on the school about whether they choose to pay for master's degrees. Other schools say we'll give you research support for the PhD, but for master's, you're going to be teaching classes and being a TA. And so there's no one prescriptive answer. It's just really depends on the school. And so one of the things you want to look for when you're applying is how do they fund their students? Some universities will fund their master's students. Many do. Not all will. Some that have thriving PhD programs won't fund their master's students because thinking about it from the PI standpoint, when you're a master's student, research-based master's is 2 years. You come in, you do classwork, a lot of classwork in the first year. You have that summer after your first year. I can get some research productivity out of you there. So then I get some in the summer from you. And then your second year, first semester, you're taking some courses. So I really only get a semester and a half uh, of um, of research, maybe 2 semesters on the high side of research productivity out of you after investing all this money in you. With a PhD student, you take classes for 2 years, then for 3+ years, you're a full-time researcher in my lab. So you have more value to me. And so you want to look at the school and see, and many of them will tell you this, if we provide funding for the master's students. Some of them will tie it to the PhD, some will do it for all graduate students. But thinking from the perspective of a PI, it's about return on investment. If I have to invest that year and a half, 2 years in you, paying you, training you, I want to get something out of it because my evaluation as a PI is on research, teaching, and service, usually in that order. And so I have to be productive in research. And if my success is linked to your success, I'm going to prefer someone I can get more years out of after I make that investment. And so I don't want to come across as harsh and tough love and all that stuff, but I just want to make you aware of what happens in the minds of these people on the other side, right? So you can tune what you're trying to do directly. So absolutely, you can find fantastic master's degrees that are paid for. I don't know off the top of my head which ones they are. Some of them might surprise you. It might be Brown that pays for them, right? But Stanford, you think Stanford, they pay for a master's? No, they don't. They expect you to pay for it yourself because they know you can get that nice job in Silicon Valley. So did I answer your question? So there's no one hard and fast rule. It's just what they do, but find out ahead of time if they pay for it. You don't want to have to pay for your master's. Yeah, question. Yes. Professionally always paying unless if you're doing it in industry, many employers will pay it for you. And in that case, it's tuition reimbursement. And I did my research-based master's part-time while working full-time. I don't recommend it. It's an exercise in time management and caffeine consumption. And what usually happens is, you take courses that semester, show them that you got a minimum grade. Usually it's B or better. And then they cut you a check for what you paid. And so many institutions, many companies will pay for your degree. I knew someone at Army Research Lab. They let you attend full time, but you have to pay it back with so many years of service, and some companies do that. Yes, you have to pay it back. Yes, yes. Because thinking about it, they spent this money on you. They want to make it back in terms of whatever the result is profit wise on the work that you do. And usually it's a one for one. You spend 5 years, they want at least 5 years out of you. Um, but yeah, so I would look at the school. Some will pay for masters and some won't. It all depends on the school. But make sure you check for that ahead of time. If a terminal master's, meaning that you're just going to end with the master's, make sure you know that ahead of time before you apply. Don't be surprised. Okay. All right. And so discipline knowledge is better. Consider the provenance, whether department grew out of the math or the engineering tradition. And then this consideration about a large school versus a small school, right? So a large school, it has its benefits and its drawbacks. A large school, you have many, many faculty who do research in the same area, right? So if you're doing machine learning, at UMass, you have someone who does multi-agent machine learning. You have machine learning and robotics, reinforcement learning machine learning. You have machine learning for NLP. You have about 10 different takes on machine learning, right? So you get those nuanced specializations when you have a large department. And so the nice thing is that it makes for a fertile environment. You can have these research groups and these reading groups and all these fertile discussions that make for a nice environment. But the problem is it's a lot less personal just because it's big, right? And smaller schools, okay, it's more intimate. The relationships are more meaningful and more personal. But you might only have one or two people in a research area. That's it. And so you have to make a trade-off. And there are medium schools that, set a nice balance in between. And so you want to see, well, do you prefer a big environment or a small environment? And it's different for each person or medium, somewhere in between. And so geographic preference. I remember when I started out, I wanted to do systems. I wanted to do distributed systems because I was doing R&D in industry before going to the PhD program. And at the time, University of Hawaii, Manoa had a killer computer networking. They did a lot of pioneering stuff in networking. But I know I didn't want to go to Hawaii, Manoa. I would never get work done. And I'd be so far away from my family that it just wasn't going to work. And you want to have ahead of time ideas of what your geographic preference is. It could be distance from home. It could be, do you want to be in the middle of the cornfields in Papillon, Nebraska, where I've actually been, and it's not much there except for corn. Wonderful people, but everything closes at 8 p.m. But nonetheless, do you want to be in a small town or a sprawling urban metropolis? Do you want to be on the coast? Do you want to be inland? Do you want to be in a city, a suburb, or the quintessential small New England small town, right? It matters your geographic preference because you're much more embedded in the community when you're a grad student. You have to live somewhere. And for an average PhD program, 5 on the low side, 8 or 9 years on the high side, you're going to be there for a long time. And a lot of the relationships between you and your colleagues in the research lab, it's blurred between professional and personal. Some of my best friends, for example, one of my former housemates from grad school, he taught the computer vision course here. He was a computer vision scientist at iRobot. Now he's somewhere else, Dr. Leeson, right? And so some of your best friends you will meet in graduate school because when you're not doing research, you're doing other stuff, right? You're going to spend a lot of time with these people, and therefore the professional, personal lines are often very blurred. What part of the country? Maybe what part of the world? You might decide, and I don't know much about Canadian grad school and European and other locations grad school, but some people choose to do grad school in another locale. Um, is it far flung or close to family? If you like to visit your family a lot, you don't want to have to hop on a plane for 12 hours just to be able to do that. So maybe it's hour driving. You can't thrive if you're not happy where you are. So you have to match where you are physically with what makes you happy, because you want to spend your time getting this work and succeeding on the academic stuff and the research. Okay. All right. Any questions? No? And so the GRE. Most want you to take the GREs, some the subject GREs. They're not fair. Guess what? Life's not fair. Invest in test prep if you can. If you're going to study for the GRE, treat it like a lab course and spend the time. Ultimately, it's easiest to do it when the bright lights of classes aren't in play, right? Over the summer, study for it, do the best you can, and just take the GREs. Also, anticipate the amount of cash you need up front to apply, right? These application fees, if you apply to 5 and 10 schools, that's going to amount. So if you have a summer internship, bank ahead some funds that you're going to have to pay 125 here, 200 there for these application fees because they can add up. And you don't want to have a choice of not applying, B, because you couldn't afford to submit the application fee. Okay. Mhm. Yeah, I'd say the summer before senior. Yeah. And so that way, you can study at the beginning of the summer, just as the semester ends. It's recommended not, I personally don't do it while you're taking classes because you're already focusing your attention between 4 or 5 different classes. You don't want to add that. You want to think of studying for the GRE like a lab course, a serious lab course, right? So you're doing lots and lots of practice from different places. You're learning words that I remember that in the English language. Is that a real word? No, that's not a real word. Sang-froid, it's French. It means cold-blooded, right? That was on the GRE, at least when I took it. But learn the game. It's a game. You just have to just do it. Go and get a lot of practice. Question. Yes, yes. The graduate record exam is the general for science, and it's not science per se, right? They do have a GRE subject test, but the GRE has verbal, it has quantitative reasoning, and then it has logic. And I don't know what they call it now. I took one of the last pencil and paper GREs, so there's a whole other game now that you have to play. They don't do that anymore? Really? Okay, interesting. Really? Interesting. So you don't have to go to the test center and they put cameras on you and yeah, yeah. Okay. 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 So you can tell when I took it a long time ago. And I remember those logic questions. John is having a dinner party, and each table seats 3 people. Mary can't sit next to John. you know, Joseph can't sit next to Sarah. And you have to like answer, oh my God, it was just a pain in the butt. But you just have to learn how to do it and you just do it. And if you can swing the fees, they're not cheap for test prep, invest in yourself, but treat it like a lab course. It's not fair. It's just a ritual. Learn how to do it, get through it, and thrive. Okay. Mhm. It's just the GRE. Of course, the grades, but also the experience behind the grades, like project work. And if you have a recurring research relationship, that's really, really good, right? Because most of your professors have colleagues all over different universities. And if so, for example, whether somebody who was a classmate of mine in grad school or somebody who was one of my advisors, if they get a recommendation from one of their own, that's going to carry a lot more weight than just an arbitrary recommendation. Moreover, if you've been doing research with someone, say from freshman or sophomore year, then you can show that progression of increasing responsibility and show that this was a meaningful relationship and that advisor can speak intelligibly in your reference about your ability as a scientist. And so going back to Nguyen Ha, she was in my lab my first year, and I had her for 2.5 years, and I was able to say all sorts of amazing stuff about her progression over time, both as my student as well as in my research lab over 2.5 years. And so I would look at the portfolio of what you've been doing, especially if it's research experiences. If you have a publication, that is really, really good because you already shown and documented that you can do research, right? And so all of the above. Did I answer your question? Yeah, sure. Ah, well, they have all these test prep books. Now they have these websites. Everyone will always take money from you, right? They have these websites that you can use. Um, I took the in-person test prep at the beginning of a summer, and then they had it was a Kaplan Center. I don't know if Kaplan's still around. And then they had this big test prep center, and you could go in and take all these GRE tests from years past. So I must have done like 20 years worth of GREs. Just every Saturday and every Friday, I would just go in and take a GRE. And that was sort of about a month before, or maybe 2 months before I was actually going to take the GRE. I just wanted to get so used to taking the GRE. So I would say massive amounts of repetition because you see all sorts of styles of questions, and it doesn't teach you anything more to do lots of repetition. It just makes you comfortable. So when you see something, you don't flip out like, oh my gosh, I don't know what table Mary should sit at. Johnson said I hated those problems. So I just do, some prep books. They have these banks of test problems. I would say do lots of problems, learn the strategies for how you eliminate stuff, and just basically learn the game and lots of practice. Did I answer your question? Yeah. There's no one prescription. Some things might work better for others. I liked to be in the prep class, and then after that, a massive amount of test questions. Um, and there's nothing more deflating. I remember at the beginning of the Kaplan course, you take a diagnostic test, and it's more so about not being used to the questions. And then I remember taking it like, oh, I guess I'm not going to grad school, right? And then at the end, you're like pulling close to perfect, right? So, and you haven't changed as a person, you just have the practice in. So I would just say lots of practice is the best thing you can do for yourself. Yeah, right. Um, so let's take a look at selecting a program. Congratulations, you got in, do your happy dance. Now it starts to get real, right? Now it's like, oh my gosh, this is really going to happen. Many big programs and some medium programs have this thing called Candidates Weekend, where they invite you to come to campus and just meet the department. And so in that, the labs will have these shows of like all the different research and demos, and you get a chance to meet the PIs, talk to the staff and the grad students. Take the opportunity when you go to a candidates weekend, it's once you've been accepted, and they'll pay for your travel and they'll feed you all this good stuff. Take the opportunity only in the casual settings, because usually the grad students will throw a party of some sort, and you'll get to meet the grad students outside of the lab. That's where you talk to them about what it's really like, right? Because you want to get a sense of the sentiment within a lab. Is it cutthroat? Is it collegial? Is it egalitarian or is it dictator style? You want to know what the culture is of the department because you want to make an assessment of how you fit into that culture in the lab in particular. And so always know that your interview ends when you come through the door, when you come back home, right? You're being interviewed during candidates weekend, but if you're going to probe the grad students about what it's like, you want to make sure it's not in front of their advisor. How much does this guy, how long does he take to students to graduate? You don't want to ask that at the university. And, casual settings say, yeah, he holds on to him for a long time, like 7 years. Um, you know, they'll never tell you that in front of their advisor, right? So you can get lots and lots of information. And so look at the advisor style. Is your advisor hands-on or hands-off? A hands-on advisor will be in the lab most days, rolling up his or her sleeves, working alongside you, asking you every day about how stuff is going. That might drive you nuts, or you might decide that's something you like, that frequent interaction. In the other extreme, hands-off, they treat you like a postdoc. They'll provide all the resources. They'll have a meeting with you at the beginning of the semester and say, all right, I'll see you at the end of the semester. And you're just kind of left on your own to figure out what to do. That works for some people. Now, coming out of industry, I was more on the preference for hands off because I knew how to do it. I just know the high level strategic stuff, and I can execute the day to day. But for some people, it's somewhere in the middle or on the extremes. So know the advisor style, and this is something that you talk to the graduate students about. And then also observe how they treat one another, not just when you're interacting with them, to gain an assessment of that culture. What are the outcomes of the research group? That's something to find out. How long do they keep their students? Some advisors keep their students for a really long time. Some you're out very quickly. What about the student placement? Do they tend to go to industry, to government, to academia? What does this lab do in terms of the landing spots for the students that graduate with graduate degrees out of this lab? What kind of funding do they have? You can find that out. Publications, they all post them, right, on their lab websites. Are they active? What about the project allocations? Are they team projects, or does everyone else have their own siloed thing that no one else touches? Right? You might want to be more collaborative. What is the lab culture? That's really, really important because you want to make sure you have the right fit. Congratulations, you got into this program, you got into this lab, but it might not be a fun environment for you, right? It's enough pressure to have something that you just don't like, right? And that's where sometimes people fail. Okay. And then the early years, you're going to get cognitive whiplash. I don't care how smart you are or how smart you think you are. Everybody in the beginning of a PhD program, you're going to find out really quickly the things you're really good at. Congratulations, keep doing it. You're also going to find out quickly the things you need to get up to speed on that you need to improve. Don't take it personally, learn it, note it, and go after it. And you'll find that everyone, it's different for everybody, various people, but don't take it personally, right? It's not a failure because there's something you're weak on and you need to improve on dramatically. That's part of the early years is to get everyone up to a certain level. And for some, and I remember there's one person, Dan Bernstein, he was really strong in the theory, but he sucked in systems and he struggled in systems. Really smart guy, but he just could not do systems to save his life. Theory, it just seemed to happen magically for him, right? And for others, it was different. And so in the beginning, amidst this cognitive whiplash, because it'll go from 0 to 100 instantly. And I remember I was in industry, took a pause before going back to school full time. As in grad school, I took calculus in high school, right? I never took it in college. Well, I took Calc 1 in high school. I took Calc 2, Calc 3, linear algebra, diffie Qs, and all that other stuff in college. But it had been a while because I got my master's and I was working in industry. And so here it is, back in school. No joke, I was spending 100 hours a week studying my first year. I studied all the time. There was stuff that I had forgotten and I needed to master, and I needed to do it from day one. I'm like, oh no, what am I going to do? So you learn what you do well. The research was just cake, right? Because I was doing R&D in industry, it just came naturally. I had the instincts. I could do experiments. I could manage projects and crank out code and build systems, analyze systems, all that stuff. And so where I had to spend more time was remembering all of that stuff on the theoretical side that I had forgotten because I didn't have exposure. And so you're going to find out this whiplash is going to go really fast. And I use whiplash specifically because it's going to be very fast. And you want to develop healthy research habits. Regardless of what classes you're taking, what you're doing, make progress in research every week. You always want to have progress. Learn the project that funds you. You want to learn its goals and objectives. Look at the history of the lab and its contributions, because that's what dictates what's important to the lab culture. Really get to know your colleagues in the lab. They will help you tremendously, but they're not going to do it if they don't know you. It could be somebody does an analysis that you need for you. Somebody helps show you how to do something, or maybe you have a paper deadline. They're helping you write the paper because they know LaTeX better than you do, right? So really get to know the lab mate. And it's not because you can get something from them, because that coin, it pays you, but it also pays your lab mates. And you'd be very surprised how someone will help you just because they know you. Learn to read research publications. It's a skill you have to learn. You're going to be reading, spending most of your time, and a recommendation is to write a survey paper that forces you to read a bunch of different papers in your area and to summarize them. You start to see the connections between these different solution approaches. And so the coursework will, in the early years, give you rigorous coverage of certain concepts. And in these graduate level courses, there's summaries. They're not going to tell you all the details. It's up to you to fill in all the details. And that's going to require you to go off and look stuff up in a math book or look stuff up in your old algorithms textbook and so forth. And so definitely work with others because this struggle is a much easier if you're doing it with other people. Some of my best friends were folks that, you stay up all night trying to get something done, helping each other out. And of course, pass your courses, no more and no less. If you're getting straight A's in all your PhD courses, that means you're not spending time in research. You want to get the minimum pass at UMass. It was an AB, which is like, 3.5 at the time when we were there. So do enough to pass your courses. Don't fail the courses, but do enough to pass them, but not more than that, because the remaining time and energy should be put into research. It's that important. Question? No? All right. And of course, when you're taking courses in those first 2 years, obviously you're not going to be spending as much time doing research. Your summers, the unwritten rule is you spend more time in the summers. Even though you're paid 20 hours a week, 40 hours a week, you're going to be spending much more than that paying back your advisor who looked the other way, funding you during the semester when you weren't really doing that much research, right? And that's an unwritten rule. Nothing will create a rift between you and your advisor sooner than going off and taking an internship over the summer when they've been paying you for 20 hours a week during the semester and you've been doing 5 hours a week of work, right? And so you always want to make sure that you're contributing back what was paid into you. Research, discuss it with the PI, start reading the relevant research literature, be an active participant in your labs meeting. When I was in grad school in the robotics lab, in any lab I've been in, come hell or high water, you don't miss the weekly lab meeting. It's just like, well, what if I miss it? No, you don't miss the weekly lab meeting. I mean, if you're deathly ill, fine. But that's where you have a paper rotation. You read and understand the paper, put a lot of time into it, make a great presentation about it, and then people ask you questions about it. And everyone's read the paper, but the person presenting is that week's expert on that particular publication. And that builds in you the skill of reading through the research literature, but being able to interpret it for others is the important skill that you're practicing. And in a lab group, you might have this rotation. It's once a week. You might have it once a month. You might have it every 6 weeks, depending on the size of the lab. But nothing is more important than participating in that effort. In the research lab. And then they'll also talk about the experiments, how it's going. People will chime in about solution approaches and all the above. Help your lab mates to succeed because that goodwill will get paid back to you at some point in the future. Do more than what is expected of you. When you do more than what's expected of you, you build trust in your advisor that whenever something needs to be done, they don't have to sit there and watch you. They know that when you say something, it's actually going to be done. And building that trust is very, very important. You pay back your semester. You're often partnered with a senior student as a first year grad student. You're typically partnered with someone who's closer to graduation, and you'll be taking over the reins of their work, right? So in the beginning, you're going to be learning a lot of stuff that's not book learning. And of course, reward yourself. Do something to celebrate those small victories. Take care of your health. It's really easy to burn out and have a lot of negative consequences on your health if you're not actively taking care of your health. Back then, I walked so many miles throughout Amherst because that's what I did. I'd go off and just walk, put on a Walkman or, like it was a Sony mini DVD player thing. That's to kind of show you the time when that was. And I would just walk. It's a beautiful area, lots of nice things to see outside, and enjoy the area where you are, right? A lot of interesting things if you choose an area that's appropriate for you. It could be an urban center or it could be rural and you go watch livestock, do livestock things, right? But enjoy the area where you are, and that makes your stay there much more pleasant. And so the apprenticeship in the midlife of your training, you pivot from book learning to research learning. And research learning is a lot more different. The classes are done. Advanced seminars are the only thing you'll probably be attending. You're going to be talking about someone's research. You might have visitors from outside come in and talk about it. You want to participate on a project and get some publications. And that's whether you're the lead on that project, working with a senior or grad student, or if you are not the lead on that project. You want to get into the publication side of it. You're pivoting from book learning to research learning, and the majority of your time after you're done with your coursework for 3, 4, 5 years is going to be spent reading the research literature. You're going to be reading paper after paper after paper after paper, and that takes time. Some of them you have to fill in the gaps and the details to reproduce it. Others, they might spell it out, but over time, you pick up all these skills. You start to learn, this group at Berkeley is doing this. This group at Brown does it that way. This is their nuanced contribution. And you're going to start to see the connections between things. That's what this research reading does. That's where you learn, right? That's building you towards making original contributions. It's also really important in this apprenticeship phase to attend a research conference because you're going to see these people whose papers you read. I remember he's a full professor of robotics at University of Michigan. I read his papers, but I didn't know the person. And I met him once at a conference, and it's like for some reason I thought I knew him, and he was kind of startled. Oh, you're Chad Jenkins. Yeah, you did this work. You're Charles Isbell. You did Lambda Cobot and Lambda Move, that paper. Well, social statistics agent. All right. Okay. But nonetheless, you're going to meet all sorts of interesting people, and you're going to have these wonderful, fruitful combinations and conversations. And these relationships that you build might turn into a postdoc or a job sometime later. You never know where this networking is going to land or revisit you in the future. So maintain those connections. And in today's age, then it was just business cards and emails, right? Today, it's social media, LinkedIn profile, and stuff like that. So it's a lot easier, but certainly make those connections. And so you're going to get more experience planning experiments. In this last bullet, don't you dare take a class. Don't you dare. And oftentimes your advisor will find out about it. And why are you taking this class? We're supposed to be working on this experiment and getting these publications. I'm not exaggerating. Because once you're done with the classwork phase, you pivot to being research learning. You said you want to get a PhD, then it's time to be a researcher and stop being a student, right? So don't you dare take a class once you enter this phase. And so develop a thick skin. You're going to have to take criticism graciously because you're going to hear time and time again that something you're doing is not quote unquote good enough. You have to develop that resiliency. Learn to talk to people and come up with solutions, not problems. And this last phrase, I know it sounds harsh. I grew up playing a lot of sports, right? And in sports, they say only your mama cares if you tried. Everyone else wants results. Learn how to get results. If there's a problem, propose the solution and get results. Because once someone can rely on you to make incremental progress, it might be slower some days, faster other days. I can count on you as a PI. If you say, I'm going to get this analysis done by the middle of the summer, I don't have to sit there and worry about, is this analysis done, right? But you have to earn that trust. Everyone wants to see results and take that seriously. Take yourself seriously. So then the proposal phase, that's when you're starting to get some scary, serious expertise. You're starting to see connections between things. You've identified gaps in practice. You can start to see a good question and you're going to write it up. And you've ensured that no one else has asked that question. And so that's when you propose your research that you want to conduct. And with that, you have to defend it, and you defend it before a scientific committee, which is your thesis committee, and they don't take it easy on you because you're asking to join their community, this community of scientists. And so you have to convince them, A, that you understand the problem, B, that you understand all the requisite body of material supporting that problem, C, how you're going to test this thing, and D, what you expect the result to be. Now, does it go 100% how you plan it? No, usually it doesn't, but you have to demonstrate that you have the maturity to be able to navigate through that path. And so that's the so-called proposal defense. And once you do the proposal defense, it's public. And this public defense is anybody who knows about it who wants to attend. So if some scientists from halfway around the world decided they're going to fly there and attend it, they could, right? And it's usually in a room. You have about 30 to 100 people proposing, watching your proposal defense. And so this proposal defense talks about how you're going to tackle the problem And you have your committee members, both quote unquote inside the department and outside the department. Outside the department are people who lend expertise to what you're doing. So if you need some statistics, it behooves you to have a statistics faculty member, a statistical scientist on your committee. If you're dealing with a robotic mechanism, maybe you might have a mechanical engineering PhD faculty member who's on your committee. If you're dealing with, for example, a computer science account for how certain reasoning happens, maybe you might have a psychologist on your committee. And so this panel of experts is a group that you assemble, and their job is to steward you through this process in proposing, and ultimately you have to defend that. You have to defend why you think this is reasonable. Now, you're gaining a level of expertise, and it's your responsibility to demonstrate who cares about this problem. You say it's an important question, you have to tell me that it's important. Who cares about it? What is the state of the art? What have other people been doing? What is your approach? And what is the impact of your approach? And you have to have metrics. You just can't say it's a good idea. You have to define for me rigorous criteria for how you measure success. And that can take some time. And so you're gaining a level of expertise. Congratulations, you passed the proposal defense. Now you're in this dangerous place called all but dissertation. Many PhDs go into the ABD phase and they never finish. It doesn't matter. I don't care what you've been doing. Nobody cares. Maybe your mom cares, but nobody cares. You have to finish. And so there's this joke that the MDs used to say, what do you call the person that barely got through their PhD program? Doctor, right? Because this ABD, and don't take my word for it, search on LinkedIn. You'll see people on their LinkedIn profile, oh, it's a computer science ABD. So you didn't finish. Nobody cares if you didn't, nobody cares about it if you didn't finish. Stick to it. And this ABD is like going on vacation. It's a nice place to visit, but don't stay there too long. You want to get it done as quickly as possible because you're not taking classes. You're not really on someone else's research project. You're focusing on your own experiments, and it's really easy to let your foot off the gas and just drift. And eventually you find a year later, I haven't made any progress, right? You want to finish. You've invested the time, you passed the proposal defense, went through all that coursework, all that whiplash, all that stuff. Just finish, get it done. And it's important to stay in that environment. Don't leave and go someplace else, which is easy to do because it's really hard to finish. Okay. All right. And so the thesis, you have a level of expertise and you've executed on your plans. You want to make sure that you're getting results. Only people care about your progress is the results they want to see. And you're meeting regularly with your advisor and your committee. Now, of course, you're executing this, and it's your responsibility to corral what you're doing with your committee. So I remember sending copies of my thesis draft via FedEx with return envelopes with the markups because email wasn't like able to do that then to all my advisors and scheduling time when it was convenient for them, for the four of them to meet with this person and then meet with that person and then meet with that person. It's your responsibility to manage it, not them. And so you want to be in constant communication because you don't want surprises to happen during your final defense. That's considered a failure in communication. So you'll eventually get the go ahead to defend. And your advisor, if it's a responsible advisor, is not going to let you get to the final thesis defense if you're not ready. Nothing is more embarrassing, both to your advisor as well as to everyone there, as somebody who's defending who's clearly not ready, right? And I would never let someone defend if I didn't think they were ready. And so getting your committee together and scheduling your defense is literally like herding cats, right? This one runs that way, this one runs that way. It's a really hard thing to schedule 4 or 5 different people for a particular date and time for an hour or 2 or 3 to do the defense. And in your defense, you are at that moment in time the world's expert in what you're talking about because it's new. It's your contribution to science. So you should act that way, right? And there are some things you might find you don't know how to and learn how to say, I don't know. This is what I understand. This is what should happen. And this is what I'll use to talk about that. Right. And so you're the world's experts. And then for the final thesis defense, you're defending it publicly. And you get lots of questions about all sorts of things. Some are relevant to what you're talking about, some are not relevant. And then at some point, you'll have a private session. And in the private session, everyone in the audience has to leave, and it's just you and your committee. That's where the gloves come off. That's where it really gets pretty harsh because they're not going to take it easy on you. You're trying to join the community of scholars, and they want to make sure you can be an independent researcher. That's really, really important. Can you make original contributions to science? You're doing it the first time, and what makes it hard is that you're learning how to do it while you're doing it, right? And so typically, you either pass it, you fail it, or you pass it with contingencies. Well, you need to do this other experiment because you didn't completely show X, Y, and Z. And the typical is path with recommendations. Very few times people fail because your advisors typically don't let you defend final defense unless you're actually ready to do it. That's considered a failure in advising. All right. And so the end game, yes. Well, if you fail, it's a structural issue, and it means that you have some fundamental flaw in your experiments and in your thinking, or you didn't do something that you outlined in the proposal. And so the question is, why did you fail? And typically, a failure means that there's somebody on your committee that you just weren't meeting with, right? If you get destroyed, so to speak, by the statistics professor on your committee, it probably means you weren't meeting with this person regularly because those issues should have been encountered and dealt with along the way, not at the end when you're defending. And so, for example, I had an advisee, I was his advisor, he's applied math PhD, and he was working on some stuff that one of his committee members disagreed with him. And so we talked about that and we had a strategy for how to mitigate that. And like clockwork during his final defense, that issue came up and he was able to just knock that out of the park and move on. And he passed. Now he's a researcher at Army Research Lab, right? And so that's just to say that you want to make sure that you don't get those surprises. And your advisor should never let you get to the final defense unless you're absolutely ready. And how you find that out is by making sure you're making full use along the way of your committee members. Because if I'm the machine learning expert on your committee, if you're doing something that doesn't, pass muster, I sure as hell am going to tell you about it before the end. And then I'm going to go to your advisor and say, this dude's not ready, right? Because of X, Y, and Z, right? You have to understand regularization if you want to carry this out, right? You just randomly, to use an example from class, you randomly chose a lag window size without even telling me why you did that. You just picked a number? What do you mean you just picked a number? You know what I mean? And so to use that example, it should be things you uncover along the way. You should never get to the end. And even as a committee member, I would, even if I'm not the committee chair, I would really push hard to cancel a defense date if I didn't think the student was ready. But there are different standards. So to answer your specific question, it should never happen. It should be addressed along the way and never get to the final defense. That's considered an advising failure across the board. Any other questions? No? So you defended, you're ready. You have to think about where you want to go, industry, government, or entrepreneurial, right? A lot of these skills you learn in a PhD are very important to hanging your own shingle, starting your own business. And there are many people who do that directly out of the PhD. Departments with big or universities with big bank accounts, they can fund a holding spot for you. They say, okay, you graduated, you need another 6 months to hang around. We'll create a postdoc for you. You can stay here, continue to do research with us for 6 months until you're ready to do this next thing. And departments with money do that. So choose wisely where you go. There are a lot of things that matter. And the skill set is very transferable. You learn how to manage people, manage schedules, manage projects, and you can teach yourself how to identify critical issues. You know how to make new contributions. And this last part I didn't understand until like 10 years out, right? You will, oops, you will get a you will get a PhD many times over in your career, right? And what I mean by that is what I did in industry as a research scientist had nothing to do with my PhD. What I did at my previous institution, the first half I was there, had nothing to do with my PhD. What I did the second half has nothing to do with my PhD. What I'm doing now had nothing to do with my PhD. The skill set of planning out, finding good questions, new questions, investigating, looking at the literature, looking at new questions and building experiments around it. That's something you learn the first time when you get your PhD, and that's what makes it hard. You're learning it while you're doing it, but then that repeats over time, right? And so after a PhD, you will get a PhD several times over in your career, right? So to speak, new contributions in interesting ways. So you'll do it many times. Thank you for listening. That's all I had to say. And hopefully this was helpful to you. I wish I knew this back then, right? I know it now. And so hopefully I can help you prevent stubbing your toe, so to speak, in those many ways that'll happen if you choose to get a PhD. And even if you never choose to enter academia or industry as a researcher, there are a lot of transferable skills. And like I said at the outset, there's no more beautiful thing in life than having choices. And this opens up choices for you in ways that you don't imagine. So I'll end there. Thank you for listening. The few, the proud, the six of you. Um, and I know this is a long period of time to listen to this, but